Okay, good morning, everyone. My name is Stefan Saroyo, and I'm a researcher in the Mobility and Networking Research Group. And it's my great pleasure to introduce to you today Yixin Luo from CMU, Carnegie Mellon, who's been working a lot on DRAM and flash reliability problems. He's an expert in this area. His work actually won a number of Best Paper Awards. He's got 2 Best Paper Awards at HPCA. HPCA stands for High Performance Computer Architecture. And he's graduating this year, and he's here visiting us. If you'd like to meet with him in the afternoon, please let me know. And there's still, I believe, 1 slot available, so it's up for grabs.
All right, thank you, Stefan.
Thank you.
So today I'm going to talk about part of my thesis research and architectural techniques for improving NAND flash memory reliability. And if you have any questions in the middle, feel free to stop me. And if you don't understand anything, feel free to stop me. Here's the agenda for today's talk. So first, I'll give some motivation and the main idea of my thesis work, and then I'll focus on introducing 2 of the 4 major contributions in my thesis, and then I'll highlight a few of the system-level implications of the work that we proposed. And then I'll spend a few minutes to talk about other works during my PhD and several future research directions that I have very interested. So the first motivation of our work is flash technology scaling. As we scale towards a higher and higher density, the flash cell size inside the flash chip becomes smaller and smaller. And this means that each individual flash cell can hold fewer electrons within itself. And this makes each flash cell more susceptible to all types of noise. And secondly, as we scaling also decreases the distance between neighboring cells. And this increases the coupling noise between neighboring cells. As a result of both effects, scaling increases the RBER error rate in newer generation of NAND flash memory. And this means that we need to tolerate these RBER errors using stronger and stronger error correcting code, or ECC code. And this leads to our second motivation, which is the ECC overhead. And ECC is very generic and it's very powerful. It's agnostic to all types of storage technology. So it works for DRAM, NAND flash, hard disk drive, or newer non-volatile memory technology. And it's powerful because it provides strong error correction and error detection guarantees. However, all of this comes at a very high cost in terms of the latency overhead, storage overhead, latency overhead, and the logic overhead of the ECC decoder. And most importantly, we find that it's not specialized to the type of error that occur on NAND flash memory. So, and it turns out that the NAND flash errors do not appear at random. So they follow certain patterns. And so we're losing a lot of opportunities to further improve the efficiency of tolerating these errors. So our goal in this work is to improve flash reliability at a low cost. And this means 2 things. For consumer class devices, this means that we want to improve lifetime at low cost. And so the lifetime is because it turns out flash memory wears out as we write or program or erase more data to the device. So this limits the flash lifetime, which is counted as the number of writes tolerable by the device. So improving flash reliability improves the flash memory's lifetime. And secondly, for enterprise class devices, which typically has a fixed which typically is replaced after a fixed number of years in data centers or in enterprise servers. And for these devices, this means that we can reduce the ECC cost while achieving the same lifetime. And this is because we can lower the RBER error rate requirement for the ECC to tolerate at the end of the fixed lifetime. So improving flash reliability means that we can lower the ECC requirement or the ECC cost. And in this work, we identify 3 new opportunities to improve reliability in a very efficient way. So first is to take advantage of the NAND flash device characteristics. So as we mentioned, NAND flash errors are not random, and there are several patterns that we can take advantage of. And second is the workload characteristics, because it turns out how the host or the workload accesses data from the NAND flash chip also affects how these errors occurs and how the pattern changes. And third is the powerful controller that already exists in all of the today's SSD drives. So this SSD controller is typically a multi-core ARM processor that is designed to handle a very high throughput workload to access the NAND flash chips. And we can take advantage of this, the idle cycles of these powerful controllers to train models and to improve reliability in the background. So here is, these opportunities leads to our main idea of making the NAND flash memory more reliable in a very efficient way by using 4 types of awareness. So the first is the access pattern awareness, and second is the flash error awareness, and third is early retention and process variation awareness, and fourth is the self-recovery and temperature awareness. And all of these has been published in recent literatures. And today I'll be mainly focusing on 2 of our most recent work, which is published this year. And these 2 works are focused on improving new types of NAND flash devices called 3D NAND and try to improve their reliability. So first I'm going to start with the third work, which is the early retention and process variation. And this is the outline of this work. So first I'll start with some background and introduction of 3D NAND, and then I'll introduce our characterization of early retention and process variation phenomena. And we propose several models of the raw bit error rate and threshold voltage of these phenomena. And then we propose several mechanisms to mitigate the 3D NAND errors. So here's the background. So on the top, I'm listing a number of works that have studied the planar NAND errors. So planar NAND errors has been relatively well studied, and these works have categorized the errors based on how they appear into several categories. However, for 3D NAND, which has been first introduced in 2013, the mass production model introduced in 2013, and up until this work, there's no 3D NAND data that are publicly available that characterize the 3D NAND errors. So we wanted to get these results through real device characterization, and this is our characterization methodology. On the bottom, I'm showing a toy diagram of our experimental setup. So this consists of a form factor SSD, which is connected to a server machine through SATA interface. And this form factor SSD consists of real 3D NAND chips, and specifically we study 30 to 39 layer MLC 3D NAND flash chips. And in this SSD, we use a modified firmware in the SSD controller that enables us to access the raw bit errors in the flash chips, as well as allowing us to change the read voltage when we read the data from the chip. And when necessary, we use a heat chamber to control the SSD temperature. And to give you some more idea of how real the data is, we collected over 180 gigabytes of highly compressed data over a time period, and then we characterized the threshold voltage, which we'll introduce later, rather than just raw bit error rate, which gives us much more information about the reliability of the device. And we also cover a wide range of error types in the 3D NAND. And we developed a lot of insights into the data through statistical modeling and analysis. So first, I'll introduce our several key points from our characterization. So the first phenomenon that we observe, and this is also unique in 3D NAND, is process variation across layers. So this diagram shows an internal organization of the flash cells within the 3D NAND chips. So each segment of this rod can be viewed as a single flash cell. And these flash cells are organized first into a bit line vertically. And if you notice, the flash cells are share the same central rod across the vertical layers. And it turns out that the manufacturing process of these flash cells causes the process variation because each bit line is manufactured by drilling a hole from the top of the flash die. And this makes the flash cell dimension to change across each layer. And this leads to different error characteristics in each layer. And in fact, this is our real characterization of this phenomenon. Yes?
I'm not very, can you comment? I'm not very familiar to this subject.
Okay.
Where is the bit stored here?
You
store some information, right?
Okay, yes, this is a good question. So basically, each flash cell holds a single unit of data. And for the device that we characterize, which are multi-level cell device, each flash cell holds 2 bits of data. And then essentially,
so over the full column, you have 2 M bits stored.
Yes, 2 M bits stored.
And can you access them independently?
We can access them each horizontal layer of flash cells are connected in word lines, and each bit, let's say the most significant bit in each flash cell on the same layer are organized into a flash page, which is typically 4 to 8 or even 16 kilobytes in size. This is the access granularity, actually the program and read granularity of the flash memory. And then all of the flash cells in the same layer, in the word line, and then all, like in this plane, in this vertical plane, are also organized together into a flash block. And then we can only erase data at the block granularity.
Okay, I see.
Yeah, and then there are like lots of these blocks in a single flash chip.
And you also said there are 2 bits per cell, and there's
Yeah.
something like most significant bit?
Yes. So for 2 bits per cell, like these 2 bits are MSB and LSB. And then it turns out that in the same word line, all of the MSB bits are organized into the same page. And then the LSB page are in a separate page. And this is how they organize data
And
here.
you can read either?
You can read either one by one, yes.
And you can do that in parallel, is it?
No, you cannot do that in parallel. But within an SSD, there are lots of these organizations, and you can access these in parallel.
So the 2 bits aren't 4 different voltage levels; they're independent cells.
Yes. About the voltage level, I will introduce later. Yeah. Yeah.
Another question: are you gonna compute on those bits, or do you just read them? Do you just do read and write sometimes?
So for NAND flash chips, you can only read and write these bits. So this is the real characterization of the layer-to-layer process variation. So on the x-axis is the normalized layer number from top to bottom, and then the y-axis is the raw bit error rate. And as I mentioned, there are 2 types of pages in the NAND flash, in the MLC flash chips, and we basically look at their raw bit error rate separately, and we make 4 major observations from this figure. So first is that the raw bit error rate varies by a lot, by as much as 21 times across different layers. And second, if we compare the 2 curves, MSB and LSB curves, we find that the MSB error rate on average is much higher than the LSB error rate, by average 2.4 times. And third, we find that the peak of the error rate of both pages appear near the middle part of the layers. and fourth, when we repeat the same experiment on a different block number and on a different chip, we find that it follows a similar trend. So this means that what we observe here about the trend is actually consistent across different chips.
So this is one device? So the first graph you showed, was that one device or a collection of devices?
So the first data, the first two curve is actually only from one block of one device.
One block of one device.
And then we also repeat the experiment on a separate device, and then compare these two results.
Same manufacturer or different?
Same manufacturer, yes. And probably the same batch. That's probably why they follow very similar. So the key takeaway here is that there is large Rabbit error rate variation across layers and across different pages.
So you're
Yes.
calling this process variation, but intuitively it seems like the layers in the middle get hottest. And that would be
yes.
why. So it's not the process of creating them, it's the operation.
It's also the process, right? Because as I mentioned on the previous slide, the reason why this happens is because how you manufacture these cells, it results in the size difference across different layers. And due to various reasons, the middle layers is more prone to the errors.
But the data doesn't support. I mean, you might be right. So the conclusion drawing that the difference in variation is due to the process changes. It might. Just sort of the data doesn't show that.
Yes, yeah, I agree. So there are actually this is essentially our hypothesis for
Right.
why it happens.
And the data is consistent with your hypothesis.
Yes, yes.
If you wanted to eliminate temperature as a confounding variable, I guess you'd have to measure the temperature of each of the.
And in each layers, yes.
But I guess you don't have to have this.
Yeah, that's too fine a granularity for us to measure. Yeah. And then the second, observation that we make from our characterization is on the retention loss phenomenon. And so the retention loss is a phenomenon of charge leakage from the flash cell over time. And on the left here, I'm showing an internal diagram of a planar NAND cell. On the right is an internal diagram of a 3D NAND cell. And essentially, these charges are stored in the floating gate of a planar NAND cell. And then they are separated by the oxide layers to prevent these charges from leaking away. And the 3D NAND cell has a similar structure, but the charges are stored in the charge trap layer. And then they're also separated by a gate oxide and the tunnel oxide, but the shape is changed drastically. So prior work has shown that retention error is the most dominant type of error in planar NAND flash memory. But now that the cell structure as well as the material used for storing the charge has been changed in 3D NAND cell. So we wonder, the question is retention error still the most dominant type of error in 3D NAND or not? And that's what we are about to find out. So this is the real characterization result of the retention error. So the x-axis is the retention time in logarithmic scale, and the y-axis is the Rabbit error rate in log scale. So here we're comparing the planar NAND retention error, which is shown in orange color, and with the blue color, which shows the 3D NAND retention errors. So we can see that the retention error actually increases even faster than the planar NAND retention errors. And what's more, we also observe that the speed of the retention loss has a very interesting phenomenon. So we can see that Rabbit error rate increases by 10 times, which is an order of magnitude, within just 3 hours after programming. And then the Rabbit error rate increases by another order of magnitude after 11 days. And then by a third and is expected to increase by a third order of magnitude after 3 years. So this means that because we care more about the order of magnitude of the robit error rate, this means that the retention errors increases very quickly immediately after programming, and then it slows down in a exponentially after some time. So this phenomenon, we call this the early retention loss phenomenon. Yes.
The dashed parts of those lines are inferred or
Yes.
extrapolated?
Yeah, it's extrapolated.
I see why for the blue line you had to extrapolate into 3 years. Why in the orange line did you have to extrapolate down to short?
Yes.
It seems like that should be the easiest.
Yes. So it's because the early retention is not a problem in planar NAND. So that's so we didn't this is from old data. So we didn't focus on the retention error that appear in a very short time after programming. So we usually care more about the long-term retention in planar NAND. That's why we didn't have the data at that time.
Do you expect it to go like that, or do you expect it to plummet even lower as it goes?
Yeah, so this is also based on a previous model that models the retention trend, essentially. So it says after the linear logarithmic transformation of the robit error rate and retention time, they should follow a similar linear trend. And it turns out that this trend applies very well for 3D NAND as well. Yeah.
Are these retention errors independent of the sort of access patterns on the device?
So retention itself is dependent on the access pattern because it depends on when you have programmed the data as well as when you read the data and how far it is from the last program time.
I guess what I meant was, is this independent of reading other cells on the device? In other words,
Yeah, so reading other cells on the device can have other effects that can affect the robit error rate.
but this graph.
But this graph, we filter out these effects, yes. So as a summary, we have observed, we have introduced two of the new phenomena that are unique in 3D NAND. One is the layer-to-layer process variation, and another is early retention loss. Yes.
So earlier you used M as the number of layers.
Yes.
What's M in practice? How many layers are there in practice?
So in the current in the generation that we characterize is 30-something layers.
30? How many?
30 to 39 layers, and then in the latest generation there are 64 layers up to 96 layers.
But the device you use, how many layers did that have?
We cannot reveal the information
Okay.
because it
Fine.
will reveal the
Sure,
identity
that's
of the.
fine, that's
Yes.
fine, okay. But it's 32 to 39 basically, and
Yes.
the number of layers grows with every generation.
Yes. Yes.
Got it.
But then, did your graph have 100 as the x-axis?
So it's normalized layer. So it's like 100%.
Oh, right, okay.
Yes. So in the paper, we also discuss another phenomenon unique in 3D NAND, which is retention interference, where the amount of retention loss in a victim cell is also correlated with the neighbor cell's states. So this new phenomena means that we need to design new mechanisms to tolerate these new phenomena in 3D NAND. And in the paper, we also have more results in terms of the threshold voltage rather than just robit error rate we show in the slides. And in the next few slides, in the next part, I will mostly focus on our approach based on these insights to develop new error models and new error mitigation mechanisms to improve its reliability. So first, I will start with error models. So here's a quick introduction of the threshold voltage distribution. And in fact, this threshold voltage distribution is what we are trying to model, and this will give us a very fundamental understanding of the reliability of the flash cell. So as I mentioned, each flash cell can hold a different amount of charge, and the charge, in fact, decides the threshold voltage of the flash cell. And each flash cell can have threshold voltage over a certain range. And in the MLC flash cell, this threshold voltage range is divided into 4 regions to represent 4 different 2-bit values. As I mentioned, the MSB bit and the LSB bits are here, and each different state there is a threshold voltage distribution, because the threshold voltage is kind of randomly distributed over a certain range. And then in order to read or distinguish between these states, we need to apply 3 different read reference voltages in order to read the bit values. But it turns out that the distribution is not perfectly separated from each other. So some of the cells may go across the read reference voltage boundary, and then these cells will generate raw bit errors. And the number of raw bit errors are decided by 2 major factors. So first is how much the distribution shifts over time. So it turns out that there are many different types of noise in NAND flash memory that can cause the distribution to shift. So for example, due to retention loss, the distribution can shift towards the left because of the charge leakage. And then this will cause more part of the distribution to overlap with the read reference voltage. And this will increase the raw bit errors. However, if we can predict how much the distribution has shifted, and then we shift the read reference voltages by the same amount, and then we can minimize the raw bit errors. And these shifted read reference voltages, we call these optimal read reference voltage. And they are typically at the boundary of 2 neighboring distributions.
This shift
Yes.
over time, is it one layer, one block, one word, the whole thing?
And
What shift?
it's every cell in the NAND flash,
Every cell.
yes, will shift until you reprogram the data or erase the data.
But each cell shifts independently.
Shifts independently. So this is our characterization of how the optimal read reference voltage changes over time. And so the x-axis is the retention time in log scale, and the y-axis is the normalized threshold voltage for each of the optimal read reference voltage. And the blue dots are the actual empirical optimal read reference voltage. And the orange dotted line shows essentially our linear model that predicts how the optimal read reference voltage changes over time. So as we can see, the empirical optimal follows a linear trend very well. So this means that early retention loss can be modeled as a simple linear function of log of retention time. And it turns out that similar trend also applies to many other parameters, including raw bit error rate and etc. So the goal is to utilize this simple linear model and within the SSD controller so that it can be applied online to improve flash reliability. So as I mentioned, it not only applies to the optimal read reference voltage, VA, VB, and VC, but it also applies to raw bit error rate as well as the mean and standard deviation of the threshold voltage distribution. And all of this can be modeled as a function of the log of retention time as well as the PE cycle count, which is the measurement of the wear out of the device, the program erase cycle count. And this is the equation. I won't go into detail. I'd just like to highlight that the modeling error rate is less than 1 voltage step for when it's modeling the optimal read reference voltage, VB and VC. So it's very accurate. And when it's used to model the other parameters, which are useful for other applications, the adjusted R-square value is very high, meaning that it fits the real data very well.
So the retention time is the time since the last program erase cycle?
Yes. Yeah.
Yeah. And how many bits do you need for retention time?
To develop this model, or
yeah, the retention time. So presumably you're going to store the retention time somewhere so that you can do this prediction. How many bits is the representation of T?
Oh yeah, so we,
Or log to, yes.
yeah, so actually, so in order to calculate the retention time, we actually only need to store the write timestamp. And then the read timestamp is essentially can change over time, right? So the write timestamp, we assume that we use Unix time or POSIX time to store it. So it uses, I think, 4 bytes of data. Yeah, and we'll mention this later. So the second model that we propose is the Robit error rate variation model that captures the process variation effect or the error rate variation effect. So in this figure, the x-axis is the per page Robit error rate, and the y-axis is probability density. So this shows the Robit error rate distribution within a single flash block. And we're showing 2 types of results. For the blue results, shows the variation agnostic VOPT, means that we apply the same read reference voltage for all of the layers. And then the orange result is a variation aware VOPT, meaning that we now apply different read reference voltages that are optimized for each layer because their characteristics are very different. And we also, so the measured results are shown in the bars. And then the curves are the fitted gamma distributions. Because, and as you can see, the real distribution fits a gamma distribution very well. And the KL divergence error of this model is very, very low.
So is higher bad or is higher good?
So higher means the higher. Oh, so higher means that there are more of the flash pages within this Robit error rate range. So this is higher. This part is higher Robit error rate,
Okay.
and this part is lower Robit error rate.
And I'm talking about the y-axis. So the
Yeah.
y-axis higher is bad, is it? Or
So this is essentially a. You can see it as a count of flash pages with this Robit error rate. Yeah, and essentially, like for example, these data means that there are very few flash pages with relatively high Robit error rate. And these pages are essentially MSB pages in the middle layers because they're less reliable, and they have much higher error rates than the average.
Oh, one more question. And
Yes.
what are the different shades of brown? Or
S-
there are 3 colors on the bars here, right? There is the blue,
yes.
the dark brown, and the light brown.
I
The-
think that's where the brown is more than the blue.
Yes, yeah, that's the kind of overlap between the two distribution. Yeah, yeah, because otherwise they are completely overlapped, and you cannot see
Got
the.
it.
Yeah. Sorry about the confusion, I guess.
And
Yeah.
what does the distribution look like, and what's its average for if you don't apply your any variation on the VOPT?
Oh yeah, so if we apply a fixed read voltage, then the distribution is actually the Robit error rate is much, much higher, and also it has a bimodal distribution, which we don't know how to explain. Basically, like it doesn't follow gamma anymore. Like it has one peak, and then there's several large number of pages with a much higher Robit error rate.
And what's the average?
The average, I don't remember the number, but it's I think it's much higher than this number. Yeah. So these are the 2 models that we proposed, and then we developed 3 new mechanisms that take advantage of this model as well as these indications of this model to improve flash reliability. So the first technique is layer variation aware reading. Yes.
Before you go to another topic, when we say Robit error rate,
Yes.
do you distinguish between a bit that is flipped inside of a cell or a readout error? You try to read a bit and you read the wrong one. And can you distinguish or? Or is
So it's basically a bit flip, but the reason why we call this Robit error is because this is not transparent to the normal user. So essentially, in the flash controller, in the SSD controller, they use a very strong and powerful ECC code to almost always correct these errors, so that all the data that you read is always correct.
so So you talk about bit error rate after correction.
No, before. This is before correction.
This is before correction.
Yeah, after correction is
It's
very, very low, like
correct.
10 to the negative 15, less than 10 to the negative
And
15.
let's say that a bit is not flipped,
Mm.
and I read it.
Yes.
What is the probability that I read the wrong bit?
Oh, yes. So this is a type of read error.
Yeah.
I think
Is it included here or not?
so. It happens very rare, and it happens very randomly. So we have a short discussion of this type of read error in the paper in the appendix, and this is mainly because of the random telegraph noise on the bit line, and it affects the sense amplifier essentially.
Okay.
Yeah, but
So
it's
negligible.
it's a fixed fraction of the errors, so it's less interesting to study these errors.
Okay.
Yeah.
Do you also take into account the read distribution of the data? For instance, some pages will get a lot of reads, which means that they go through a lot of read disturbance.
Oh yeah. So this doesn't consider like redisturb because this is essentially a design experiment, and so the only reads that appears on these flash blocks, on these flash pages, are the reads from the characterization itself.
So, what do you think how would you go about using something like this in the real world? There are obviously reads going to be present. How would you
Yeah.
do this at runtime?
Yes. So so whenever there are other types of errors, for example, redisturb or retention errors, I would think that distribution will still follow a gamma distribution if you apply the optimal read voltage, or like close to the gamma distribution. But the parameters may be different because the error rate may increase, right? And however, there is also a very interesting case of how this trend of process variation affect the sensitivity to redisturb and retention, right? So maybe like, for example, these worst case layers, they are also more prone to redisturb, and then they increase faster. Yeah. And this is like we have in mind for future work. Yes. So as I mentioned, this layer variation aware reading, or LAVAR, is designed to mitigate the layer-to-layer process variation problem. And specifically, we try to target the problem where the error characteristics or the read reference voltage is different in each layer. So the goal is to adjust the read reference voltage for each layer. And the way how we do this is essentially learn an offset for each layer and then add this offset to a layer agnostic VOPT. So this offset requires to be learned only once for each chip because the process variation is consistent across PE cycles, across its lifetime, and this requires 2 times a layer number of bytes of memory for each chip. And then the layer agnostic VOPT can be, there are many existing mechanisms that can predict this value. And on average, LAVAR reduces the RBER error rate by 43%. And then the second mechanism that we propose is layer interleaved rate, or Lee rate. And this is also try to tolerate layer-to-layer process variation, but this tries to target to mitigate the worst case RBER error rate. So it turns out that these worst case RBER error rate will limit the lifetime of the device. That's why they're really important. And the key idea is very simple. Essentially, we want to group the flash pages with a much higher RBER error rate with other pages with much lower RBER error rate so that we can average their reliability. So we'll talk about how we reorganize the RAID layout in order to eliminate the worst case. And this requires only less than 0.8% of the storage overhead. So to give you a quick refresh of how conventional RAID is applied on enterprise class SSD. And this is a diagram that shows it. So essentially, conventional RAID is deployed on enterprise SSD to tolerate chip-to-chip process variation. So if one chip has very high robit error rate or is very likely to fail, we essentially group together flash pages from multiple flash chips, so that one of the chip has failed, we can still recover its data by reading all of the other flash pages within the same group, and then recover its value by calculating the parity. However, this creates a problem because we're grouping together flash pages on the same layer. This means that this worst case, there can be a worst case group that are most likely to fail. And then this limits the flash lifetime, because if this group has failed, we have to retire the entire flash block. And then this will reduce the capacity of the enterprise drive very quickly. So the idea of layer interleaved RAID is essentially we try to also interleave across different layers. So for example, group 0 now contains flash pages in word line 0, as well as word line 1, word line 2, and then word line 3. And also it consists of pages both from MSB page and from LSB page. So now if we look at, for example, the worst case page in layer 2, if this page has failed, we can recover its data by reading from the same group but on different layers. So in this case, it will improve essentially improve the reliability. And overall, this reduces the worst case robit error rate by 66.9% compared to the conventional rate. And the third mechanism is retention-aware reading, or REMAR. And this is trying to target early retention loss phenomenon, where the threshold voltage shifts very quickly after programming. So we need to adjust the read reference voltage also very quickly based on the retention loss. And the key idea is very simple. Essentially, we learn this retention loss model online and then use this to predict the optimal read voltage. We periodically characterize randomly selected flash blocks in order to read this retention loss model. And then, as I mentioned, the retention time can be calculated by subtracting the read timestamp by the write timestamp. And the write timestamp is stored at the block granularity, and this requires 800 kilobytes of memory for the entire chip. And essentially, we use the model to predict the VOPT. And this reduces the robit error rate on average by 51.9%. So all three of the mechanisms can be combined together to further improve flash reliability. And this is the result that shows how much reliability can be improved. So on the x-axis is the P cycle count, which shows the wear out, and the y-axis is the worst case robit error rate. So and the purple curve shows the ECC limit that the error correcting code can tolerate. So because of wear out, the error rate keeps increasing over time, and then after some time, the ECC can no longer correct all of the errors, and then the SSD can no longer reliably operate. So the black curve shows the baseline, which uses a fixed read reference voltage, and the red curve shows the state-of-the-art technique to predict the optimal read voltage. And then ignore the two other lines, but look at the orange line, which shows the combined error rate of all three of the mechanisms, which we call this work. So as we can see, this work, when combining all three mechanisms, can improve flash lifetime by 85%. And then if we keep the lifetime the same, we can lower the ECC storage overhead by 79%, which is a lot. So the key takeaway here is that all three of the mechanisms, they can be combined to improve flash lifetime or reduce ECC overhead very significantly.
So all of this curves use RAID?
Yes, assuming RAID, yes.
you say lifetime, you said it at the beginning, but I'm not sure. You store some bits and you want to recover those same bits.
Yes.
after some
Yes.
amount of time? Okay. But
Yes.
if you reset your memory, it's still usable.
What do you mean reset the memory?
If I want to store some new information, I erase everything. I want to keep using my memory. It's still working, right?
Yes, it's still working.
It's the maximum amount of time for which I can store a given information.
So it's a maximum amount of time. So the x-axis is a program cycle, meaning that after you program certain amount of time, the device is worn out to an extent where you can no longer guarantee that the data you store on it next can still be reliable.
Okay, so it's the device. Even if I reset
It's a device, yes.
Okay.
Even if you reset it and then you program new data, it's not reliable anymore.
Okay.
Yeah. Yes.
Yeah, so you mentioned that you have to maintain, I think, roughly 800K of state to know the retention time.
Yes.
For each block. Are there any other sort of trade-offs I have to make to increase the lifetime of my device? I have to store this extra state. Are there other things? Are there computational overheads?
Oh yes, yeah. So there are a few because we need to learn this model offline, but this is mainly targeting for like enterprise class devices, which usually have like an idle phase, where you can utilize the idle cycles to perform this characterization, which involves quite a few amount of reads from the device. And if you can schedule it wisely, then it won't cause interference to the workload.
So like roughly how long do you think it would take a device to come up with a model that would achieve
Yeah.
this?
So if you do this continuously, it will be a couple of seconds to a couple of minutes. Yeah.
Can I also ask something?
Yes.
And these lines are from the.
Ba-
So what is the methodology? Like how many devices
Yes.
you use for these lines?
Yeah. So this is based on the model of the distribution, model of the flash cell, based on our real characterization results. That's why there are fluctuations.
But so I understand the fluctuation, but I don't understand why it goes down at all. Like as you increase the cycle count.
Yeah, that's because of the fluctuation, right? So because the error rate is not like a static. Like if you have, for example, consecutive P cycles, they should have similar reliability,
I
but
see. We might
maybe
start
some,
from again.
yeah.
And my other question is, these timestamps, where do you store them?
So store them we have to store them persistently in the NAND flash memory, but we also need to cache them or like fetch them into the DRAM in order to, so that you can very quickly calculate its retention time during a read.
And those pages are subject to the same voltage
Ye-
dynamism?
Yes, but these are like protected by ECC, so all the data that you read will be reliable.
Huh, it seems like some of the least valued. Who cares about reading that?
Yeah,
reliably?
that's also, yeah. You can tolerate some errors in these data. So we have introduced 3 of the mechanisms, and we have look at their improvement in terms of lifetime. And in the paper, we also designed another mechanism called RENAC, which is designed to tolerate the retention interference phenomenon. So in conclusion, 3D NAND error characteristics are not well studied, and we perform some characterization to understand and mitigate these errors. So we also propose several models that are very accurate, and then we discuss 3 mechanisms and evaluate them and show that they are improved lifetime. So are there any questions so far? Yes.
Yeah, as you've evaluated successive generations of these 3D NAND devices, have you found some things that the manufacturers have fixed, some characteristics that have changed dramatically?
Yeah, actually, so we, because this is like the only generation that we can have access to at this point. So we haven't looked at the data for 64 layer, for example.
Okay, you mentioned
Not yet.
64 layers, so I thought
Yeah.
maybe you had some fresh off the presses.
Yeah, not yet. Yeah, because it's 64 layer is also relatively new. I think the devices are out this year mainly. So as I mentioned in the previous section, that early retention error is the most dominant type of error in 3D NAND. It's even worse than planar NAND. So that's why in the next work we focus on mitigating these retention errors by taking advantage of self-recovery and temperature effects, and we'll introduce this later. So here's the outline for the second work. So I'll first give some introduction of these two effects, and then I'll introduce some characterization of these two effects. And then we propose a model called the URT model, which is Unified Self-Recovery and Temperature, that captures these two effects. And then we propose a mechanism called HeatWatch that utilizes this model to improve the 3D NAND reliability. So as I mentioned, the flash cell holds a charge to represent different data, and then if you remember, the oxide layers are essentially insulators that prevent these charges from leaking away. However, this insulator has a problem because as you program or erase more and more during program or erase operation, you need to force these electrons to enter or exit the flash cell, and this will need to go through the insulator, and this will create stress on the insulator, and this creates a wear out. And this wear out has two major consequences. So first is that it will accelerate retention loss, which is charge leakage over time. So as the insulator becomes damaged, some charges can be trapped inside the insulator, and this will create pathways for other charges to leak away from the insulator. So this will essentially create more and more errors into the flash device. And second effect is the program variation effect. So program variation is the initial voltage difference between the lowest and highest voltage states. So essentially the threshold voltage range. As the insulator becomes damaged and more charge gets trapped within the insulator, it increases the threshold voltage of the lowest voltage state. And this makes it harder to distinguish between neighboring states. So as a result of both of these effects, wear out introduces more and more errors into the flash device. And these errors will limit the flash memory lifetime. And in this work, we mainly exploit two ways to improve flash lifetime, and their self-recovery and temperature effects. And I'll introduce these two effects in the next few slides. So first is the self-recovery effect, which is a phenomenon of the flash cell that can partially repair its own damage due to wear out. And the self-recovery happens during the dwell time, which is the idle time between consecutive program or erase cycles. So it turns out the self-recovery is correlated with the dwell time. So if you have a longer dwell time, it means that the flash cell can recover even more. And this more recovery means that you can reduce the speed of retention loss dramatically. And the second effect is the temperature effect. So from a physics point of view, essentially higher temperature increases the electron mobility within the flash cell. And this means two things. During program time, a higher program temperature means that you can program or erase more electrons to or from the flash cell. And this increases the program variation because it increases the difference between highest voltage and lowest voltage state. And this is good for reliability. And however, during storage time, a higher temperature means that it will increase the electron mobility within the flash cell, and then these charges are more likely to leak away over time. So this will accelerate the retention loss phenomenon, which is bad. So as we mentioned, self-recovery and temperature and different temperature, they affect flash reliability in many different ways. And very few work has studied these two effects in planar NAND, and these two effects are completely unreported in 3D NAND before our work. So that's why we wanted to also perform a characterization in order to fully understand these two effects in 3D NAND. So the metric that we use for our characterization is first is the retention loss speed, which measures how fast the voltage shifts over retention time. And the second metric is the program variation, which is the initial voltage difference between highest and lowest voltage state. And essentially, we focus on how self-recovery affects retention loss speed, as well as how temperature affects both retention loss speed and program variation. And I'll introduce the results later. But essentially, the self-recovery doesn't have a lot of effect on the program variation, and that's why we don't study them. So first is the result for the self-recovery effect. So the x-axis is the dwell time, and it's essentially correlated with how much self-recovery you have on the flash cells. And the y-axis is retention loss speed. So the result shows that increasing the dwell time from 1 minute to 2.3 hours will slow down the retention loss speed by 40%. And this is quite a lot of reduction. And the second result shows the program temperature effect. So the x-axis is the program temperature, meaning the temperature during the program operation. And then the y-axis is the program variation. And if you recall, it's the voltage difference between highest and voltage states, right? And this result shows that increasing program temperature from 0 to 70 degrees Celsius improves program variation by 21%. And then the third result is for storage temperature effect. So the x-axis is the storage temperature, the y-axis is retention loss speed. And this result shows that lowering the storage temperature from 70 degrees Celsius to 0 slows down retention loss speed by 58%, which is also a huge amount. So as a summary, we have shown that these three effects, they change flash reliability in many different ways. So next, we are going to propose a unified model of all of these effects called URT.
Can you give us
Yes.
some intuition about what's happening during that dwelling time? Like, what's like, it sounds magic.
Yes.
I want my program
Yeah.
to self-recover.
Yes, that's a very, very good question. So essentially, as I mentioned, wear out is caused by this damage, and then some more charged electrons will be trapped within the insulator, and this causes a lot of problem. So it turns out during self-recovery or dwell time, these charges that are trapped in the insulator can be randomly detrapped over time. And this not only removes pathway for charge leakage, but also reduces actually improves the, it changes the program variation a little bit.
And the device actually doesn't even have to be powered for these electrons to escape this trap.
Yes, it doesn't have to be powered. And actually,
But does it have a correlation with whether you're using your SSD, with how intensively you're using your SSD? For example, if I'm issuing many operations to the SSD, does it take a longer time to recover, and if I leave my SSD idle but on, does it recover quickly? Is there some correlation with that, or?
So read. So essentially, read doesn't affect the self, but write affect, because essentially the dwell time is defined as the interval between consecutive writes, right? By the way, the charge detrapping is only a temporary effect. So if you program and erase a new cycle, then maybe the previously detrapped place location is again there is an electron trapped. Yeah. So next I'll go into our model, which is the Unified Self-Recovery and Temperature Model, URT. So this model can capture the mean threshold voltage as well as the optimal read reference voltage. Essentially, it models how the voltage shifts over time. And this predicts these voltages as the sum of initial voltage before retention, which captures program variation, and the voltage shift due to retention loss or retention shift. And this model can be broken down into 3 components. The first, the initial voltage before retention, is predicted by a program variation component. And the retention shift is first predicted by a self-recovery and the retention component. And then this component is scaled by a temperature scaling component. And I'll introduce these 3 components one by one. So first is the program variation component. So so this is essentially an existing model before our work. And according to our characterization, we show that the program temperature affects the initial voltage dramatically. That's why we add this parameter to this model. And this is how the equation looks like. So I'd just like to highlight that we validate our results using our real characterization data and show that it fits the real data very well. And then the second component is the self-recovery and the retention component. So again, we, according to our characterization, the dwell time or the self-recovery affects the retention shift dramatically. And we add this component to an existing model. And through our validation, we show that our new model is 3 times more accurate than the state-of-the-art model when it's used to characterize 3D NAND reliability. And then the third component is the temperature scaling component. And this component utilizes an Arrhenius equation, which is originally used to scale the chemical reaction speed under different temperatures. But it turns out that it also applies very well to NAND flash devices. So we use this equation to scale the actual retention time and the actual dwell time under different temperatures into an effective retention and dwell time under room temperature. And through our validation, we find that we need to adjust an important parameter called EA, or the activation energy, from 1.1 electron volt, which are previously used for planar NAND, to now 1.04 electron volt for 3D NAND devices. So overall, when we combine these components together, the overall model has a very low prediction error rate of 4.9% when it's used to predict the optimal read voltage. Then we use this model to develop a mechanism called HeatWatch. And the key idea is actually very, very simple. We predict the change in the threshold voltage distribution using the model, and then apply a near optimal read reference voltage. And here is the overview of this model, of this mechanism. HeatWatch consists of 3 tracking components and 2 prediction components. And the tracking components provides the input parameters for our model. And then the model can, the prediction component utilizes this model to predict the VOPT. And then it also feeds back into the model to make it more accurate over time. So the first tracking component is tracking the SSD temperature. We leverage existing sensors in the SSD to measure the temperature. And then we pre-compute the temperature scaling factor based on our temperature scaling model at a logarithmic time interval, and then store these pre-computed values. And this allows us to minimize the repeated computation and accelerates the process. And this tracking dwell time requires us to only log the timestamp of the last 20 full drive writes. And this is because our characterization shows that the self-recovery effect diminishes after 20 PE cycles because it's a relatively temporary effect. And the third component is a PE cycle and retention time tracking component, This is essentially the same as the REMAR technique, where we log the write timestamp for each flash block and then calculate the retention time by doing subtraction. And then the first prediction component is very straightforward. Essentially, it calculates URT using the tracked information, and then it has very high accuracy. And then the second prediction component essentially fine-tunes the URT parameters in the background. And this allows us to accommodate to chip-to-chip process variation, because we can learn a different set of parameter for each flash chip. And to minimize their overhead, we use periodic sampling to sample a small number of flash blocks within each chip, and perform some characterization to minimize its overhead. So overall, this mechanism, HeatWatch, is very low overhead. It uses less than 0.16% of DRAM in a 1 terabyte SSD, and then the latency overhead of the prediction component is only less than 1% of the flash read latency. So we also evaluate HeatWatch using based on real workload traces, and this is essentially MSR Cambridge trace, which are like several different server traces that provides us with the real dwell time and retention time values of the real workload. And then we use a temperature model based on a trigonometric function that represents the periodic temperature variation within a data center. And then we add some Gaussian noise to include some small transient temperature variation due to a potential CPU surge. So again, this is the lifetime results. The x-axis is a PE cycle count, and the y-axis is the Rabbit error rate. And the purple curve is the ECC limit. And the blue curve now is the baseline, which uses a fixed read reference voltage. And the orange curve is the state-of-the-art, which is essentially the same as REMAR technique that we previously proposed. And then the green curve shows the HeatWatch technique. And the red curve shows the ideal case where we can magically know the actual optimal read reference voltage without any overhead. So as we can see, the HeatWatch improves lifetime by 3.085 times over the baseline. And then it improves by 24% over the state-of-the-art technique. So overall, HeatWatch improves lifetime by capturing the combined effect of retention, wear-out, self-recovery, and temperature altogether. So in conclusion, 3D NAND flash memory is susceptible to early retention error, and we perform experimental characterization of self-recovery and temperature, which both affect retention error significantly. And then we propose a URT model that is highly accurate, and then we develop a new mechanism called HeatWatch to improve lifetime significantly. So any questions so far regarding HeatWatch? Okay. So this goes back to all four of our contribution. So in the past, I've also worked on WARM, which take advantage of the write hotness of the workload to relax the retention requirement, and this also improves lifetime significantly. And I've also looked at online flash channel modeling, which essentially develop models for planar NAND cell, and also develop several applications that can take advantage of this model. So overall, the system level implication has essentially two categories. One is that improves the device lifetime very significantly. And all four works, they improve lifetime very significantly. And in terms of ECC cost, all four of the work, except for WARM, the three later work improves ECC cost very significantly. So in conclusion, we have looked at the 3D NAND error, and including the three techniques that we propose that take advantage of the device characteristics. And we also look at HeatWatch which take advantage of the workload characteristics like retention time, as well as the dwell time, as well as even temperature of the SSD. And the worm take advantage of the write hotness of the data, which is a workload pattern. And both HeatWatch and online flash channel modeling utilizes the powerful controller to develop models. And in terms of industry impact, we have sources from industry that confirms that 3D NAND retention problems requires threshold voltage tuning like HeatWatch. And similar background tags like we develop will be used in the next generation product to improve its reliability. And hot cold data separation is now widely adopted in the FTL or the SSD controller to improve the efficiency. So that wraps up my like the introduction of the main talk. So next I'll go through my other works during PhD and several future research directions that I have in mind. Yes.
How many more slides?
Just two, three more slides. Yeah.
We're running out of time.
Oh, okay. Sorry about that.
No, it's all right.
So just very quickly go over, I've also collaborated with many others on other flash reliability and SSD scheduling work. And earlier during my PhD, I've interned here and developed a heterogeneous reliability memory, which tries to balance the reliability and the cost in data centers. Yeah. And future research directions, so I think it will be interesting to further look at how to utilize characterization data to improve storage reliability and performance, and also design better storage to help processing larger amounts of data. And I think it's also very interesting to look at database or look at how to accommodate non-volatile memory for databases. So that's all. Yeah.
Okay, thank you.
Thank you.
So I have sort of an open-ended question. I mean, I'm not an expert in this area, but it seems to me like, so this kind of work, and you mentioned this, is really aiming at improving the SSD storage for enterprises.
Yes.
And, big class of enterprises, especially the kind of that Microsoft cares about, is the cloud. It's sort of, the servers in the cloud. And
Yes.
Imagine that in the cloud, what cloud operators would really like is the ability to program their SSD controllers.
Okay.
And to sort of understand, because they can say, oh, these are compute nodes and these are storage nodes,
Yeah.
and for these things I care about this, and for this I care about that. And I also understand there is some sort of effort to make an open implementation of the SSD controller.
Mm.
Am I right? Since you worked in this
Okay.
area, can you
Yeah,
elaborate more on that, or like where is the industry going, or is just to expect that to, or is just going to be sort of an effort on the side that is going to fizzle out?
Yeah, so that's actually, so one of the work that I have in mind is, so right now there is a huge discussion of this open channel SSD or Project Denalo, something in Microsoft. Essentially, and this is essentially we want to decouple some of the functionality from the flash controller to the host CPU. And this is because we find that there are inefficiencies in the host system design, because the file system usually utilize a log structure file system that maps from file namespace and maybe the file offset into a logical block address. And then the FTL or the flash translation layer in the SSD controller again maps from logical block address to the physical locations on the flash memory. And each of these mappings are non-transparent to each other.
Right.
And this makes it lose information on both sides. So on the SSD side, you don't know about the workload situation. For example, you don't know if this LBA and that LBA, they actually storing the same data but different versions. But on the and also on the operating system side, the file system side, you don't know whether it will be mapped to this flash channel versus that flash channel.
Right.
And this affects performance a lot, and this
Right.
loses a lot of the efficiencies.
Right.
And also another inefficiency is the mapping overhead, because you need to store large mapping metadata for both maps. So that's why the open channel SSD is trying to move this part of management up onto the system and maybe potentially merge them together and leave the reliability management inside the SSD controller. Yeah, because it's more tightly coupled with the ECC unit, as well as the requires more knowledge
Right.
of the flash device itself.
Can I ask,
Yes.
what you didn't mention, what kind of error correction is used? What kind of code is used?
Yeah, so in the current generation is LDPC, low density parity code, parity check code.
Okay. And do you know roughly what the length and the distance, the minimum distance of the code?
So it can, so LDPC is kind of, if you use soft decoding, there's not a fixed guaranteed number of bits that it can correct.
Okay.
But in the previous generation, which uses the BCH code, which typically can correct maybe 40 to 80 bits of error per 1 kilobyte.
Okay. And that means if I go back to this diagram, this picture,
Yes.
how many cells do you encode together in a single block?
What do you mean?
To have a BCH code with distance 40, you have a length that is a few hundred, so you encode a few hundred bits or a few thousand bits together.
Oh, you mean the granularity of the ECC protection?
Yes.
Oh yeah, so like a flash page is like maybe let's say 8 kilobyte, but this is usually divided into tens of code words.
Okay.
Yeah, so maybe the size will end up being maybe a couple hundred bytes
Okay. So the encoding is within a page.
within a page. Yes.
Okay.
Okay, thank you very much.
Okay.